All right, good morning. So today will be the last class, and we definitely will have some review session for you. I'll reach out to you on e-class to see which date and which time might be better for you, and then we can maybe answer your questions related to the exam. But that's for later. Since your exam is scheduled to be pretty late later, I'll talk about your exam as well today. But let me just mention very quickly. If you're still interested going over your programming test number 1 solution, reach out to me. I still have office hour today and also tomorrow. And starting from next week, I'm not too sure if I will have office hour since we got review session. We'll see. If I do have one, I'll let you know. Otherwise, take advantage, right? If you want to go over your programming test 1 and get some feedback. And your assignment number 4 has been released. It will be the last assignments. So this one here is similar to assignment number 3, but instead we are trying to use the link structure of the node to implement some algorithm. So I think that'll be some useful way to actually see how useful what you learn in this course can be, right? Just an example. It's not very difficult, pretty light. I think that'll be beneficial for your learning. Submit it in time and your best effort. And concept over there may be covered in the exam, right? I'll talk about the exam. And I will release some PDF guide later today. I do have some preliminary draft about your exam information. I'll go over that with you maybe after the break. So for the first 1 hour or so today, I will cover a little bit more material, and then there will be certain parts we can assign to you as a makeup lecture, just about the heap and heap sort. That concept there is also very useful before you finish the course. All right, guys, any questions before I talk about some binary search tree to finish off? All right, so if you don't mind today, maybe we'll have to break slightly later than usual. And today, last class, there's no need to take any attendance. So I'm going to calculate your attendance bonus when I calculate your final grades. Everything has been recorded on the iClicker, so nothing to worry. Okay, so let's now talk about the stuff. And so far, we talk about lots of details about binary search tree. Right, so this is what you have to recall. So instead of recap, this is what you have to go back and check. So binary search tree. So what is the so-called search property? And also, what is the so-called sorting property? And of course, whenever you talk about the sorting property, you have to talk about it together with in-order traversal. And we have to revisit this sorting property today as well. Okay, we'll see. Especially for deletion, you have to make sure when you delete a node from a tree, you don't delete it in a way that's going to compromise the sorting property or search property. That's something we'll see. In order traversal. And we also talk about searching. We spent quite a bit of time last Wednesday about searching. So searching here, you can definitely look through the algorithm. Of course, it is recursive. And what's really important is about running time over here. Okay? So there are basically 3 possible ways to express the running time. You have to be very careful about which one should be chosen. The most accurate should be big O of the height of the tree. Right? To see why, you should really go back to the lecture and review. Okay? And the best case will be big O of log n. And the worst case will be if the tree happens to be pretty much linearly slanted. In that way, it will be big O of n, where n is the number of nodes in the tree. All right, so these are the 3 running times that we discussed thoroughly last time. Make sure you understand, not just to memorize them. So for the actual exam, you're going to write in about more than 2 weeks' time. The last thing you want to do is just memorize about the definition and running times. You really want to understand what's going on for each data structure, so you will be able to apply your knowledge to new problems, which I'm going to give to you during the exam. All right, so that's pretty much, let me say one more thing. And of course, we'll talk about insertion. Insertion. Of course, part of it is simply searching. Right, we got 2 cases. Either the search was unsuccessful and versus the search was successful. And how are these 2 cases are going to be dealt differently when you do insertion, right? Review them. That's something we discussed as well. All right? And apart from this, any questions about what we discussed last time? About any basic clarification of binary search tree. Okay? Okay. So why don't we move on to talk about the last bits of binary search, which is about how you can delete nodes from the tree. Okay, let's talk about it. We talked about two cases already. Okay, let me just show to you. When you actually go over the slides, you will see this slide here, slide number 19, about deletion. We talk about case number 1 and case number 2. Okay, so these two. These two are the very straightforward cases to really handle. Let me review them very quickly. Let's say, for example, I want to delete the node with key 31. After the series of searching, I found that 31 doesn't really exist. In that way, nothing to delete. Easy. Okay? The second case was, let's say I want to delete a node with key 80. In that case, 80 is over here. It does exist. It's there. In that case, we are also lucky because both child nodes over here are simply external. So we can simply delete this node by converting it into just external. That's the way to delete, and nothing will be compromised. Okay? So these two cases are the easy ones that we finished last time. Question? So we say it again, the external nodes over here. Oh yeah, so of course, when I say you want to turn this one here to be external, of course you should really set the left and right to be null at the same time, right? That's kind of the byproduct of converting that into external, okay? All right, so that's about the two simple cases. And today we're going to talk about the trickier cases. We got another two, okay? Let's take a look one by one. By the principle of doing deletion from binary search tree, two principles. Number one, you have to do searching, like what you did for insertion. Number two, when you try to delete, you have to make sure you want to do it in a way that's not going to compromise the searching property. These are the two principles, and we'll see how we can satisfy these two when we do the two cases. All right, case number 3. That's what you will see on the slides. We found the nodes that we want to delete. Let's call the node P, okay, for now. Sorry, let me just find my cursor over here. Let's say the node we want to delete is called P. And it's not a case that both child nodes of P are external. One of them, just exactly one of them, is internal. In this case, what should we do? Let's look at the diagram. Okay, over here. All right, for this particular tree, we want to delete, let's say, 32. Let's find 32 very quickly. Okay, so let's say I start with the root 32, less than that. I will go over here, and 32 larger than that. So there we go, over here. So this is what we call P. That's on your slides. This is the node that we want to delete. In this case, what should we do in order to delete it? It's also not too bad because you can see this is an external node over here, and this is an internal node. Different from when both nodes are external. Okay? The way to think about it is it possible to simply delete this right away and leave a gap? No, that's not the way to go. Somehow you will have to do some reconnection of the tree. Okay? I'll mention that diagrammatically first and see how we can do it. All right, let's see how we should do on the bullet points. All right, R sibling is external. So R that you see over there is here, the child node. The child of P that itself is not null, right? And then replace the node P by node R. That's why you got to do some replacement. Okay? So what you do is think about what's going to happen is you're actually going to basically think about rather than connecting this way. So this will be number 1. Oh, let me use a different color. Rather than connecting this way, you're going to connect this way. This will be number 2. And then you can delete this node. That's number 3. Okay, so these are the 3 steps. Of course, I'm just annotating the steps using the diagram. When you have to implement this, you have to write in Java code, which just by setting parents, by setting child nodes. That's basically what you got to do. But let's justify this step very quickly. Okay, if you look at case number 3, okay, This is how you should think of it. And we'll do similar justification for all the later cases. Before, let's say, before deleting 32. What's the in-order traversal roughly like? Okay? And for this one here, since you can see it's heavily involving this particular subtree, why don't we try to do in-order traversal just for this left subtree? And this part over here is untouched, so that part here is not going to be changed, right? So why don't we look at the in-order traversal for this part, okay, before the deletion? It's basically 8, 17, 21, 28, and then 29, 32, 44, and then ... etc. Okay, that's the in-order traversal before the deletion. What we're doing over here is we are going to remove this node by following the 1, 2, 3 different steps, and what we got is 32 should be gone. What if we try to do in-order traversal once more? Let's say after deleting 32. So what should we get? You're still going to get 8, 17, 21, 28, 29, and then 44. Agree? So it would be as if you delete just over here. Okay, kind of follow my point? You're going to think about the in-order traversal before the deletion and after the deletion. What we are basically doing is we're just removing one node, which is 32, from the linear order. In that case, is the resulting sequence still sorted? Indeed. So the search property is maintained, or the sorting property is maintained. All right, so that's case number 3. All right, any question? Okay? So again, let me remind you about the 2 principles. You want to make sure you do the search to the node you want to delete. Once you have deleted the node, this doesn't matter which case we're dealing with. We have done 3 cases. We're going to do another 2 cases very quickly. Once you have deleted a node, you have to make sure the sorting order will still be maintained, even though one node has been deleted. Right? That's the principle. Okay? Any question about this? Okay, what you should really try to do, which is some kind of easy exercise. Okay, again, you got all the source code available to you, so the exercise you should do is implement case number 3. Okay, to see how you can implement this case. Basically, starting from the searching, and then you check to see whether it's really matching case number 3. When the node that's returned from the searching has one child node is internal, and the other child is external. That's the matching case. And then how you can follow step 1, 2, and 3. Okay, that's what you should do in Java. Okay. All right, if no question, then I'm going to move on. So that's case number 3. And you can see I always put this question over here. Is it still a binary search tree? So don't be too surprised if I ask you in the exam. I might say, now, handle this case for the deletion. And you write down the steps, either in Java or maybe in English. And then I might have another answer box for you to say, justify why that deletion is appropriate. How do you justify? You have to use a sorting property, as I did on the page. Right? So you got to practice. You want to justify the deletion steps. So here you can see you got 1, 2, 3 different steps. Together it's going to delete node 32. And then the way to justify that being appropriate is by looking at the before and after sorting order to see if the sorting order is compromised. If it is not, then it's appropriate. Okay? Yes, indeed, it's still binary search tree. Yes. Okay. All right, the next one. The case number 4. So this is trickier. There will be 2 subcases I would like to show to you. Both nodes are internal for the node that we want to delete. To be more precise, the node that we want to delete, both of its child nodes are there. So it's not that straightforward to delete right away. you gotta do a little bit massaging in this case. Let me show you the complication here. Okay, let's look at the example right away. Okay, the slides show to you the precise steps to follow, but let's now see why we should do that way. Okay, I divided into point 1 and point 2. Okay, let's look at both at the same time to see which node we want to delete. Let's say we start with 44, and 17 is less than that, so this is the node that we want to delete. Okay, so this is the P. You can see it does have some left subtree, it also has some right subtree. So it's definitely more complicated than before. Okay, let's see the subcase number 2. Let's say we start with 44 over here, and we want to delete 88. 88 is larger than that, so we're going to delete this one here. And this is the P that we want to delete. You can see again, it also has left and right subtrees. Again, definitely more complicated than before. So how are we supposed to delete this node over here? If we simply delete this and simply delete this, then we got 2 trees that has no parents, which is pretty bad. You don't want to do that. All right? I want to lead you guys to some sensible solution. I can tell you that there are at least 2 possible solutions to deal with this deletion here. But let's understand why. Okay? Remember the second principle I said. After the deletion, it should be done in such a way that the sorting property is still maintained. Let's follow that hints before I present to you the solution. Okay? Why don't we do for this one here? That might be a little bit easier for you to see. Okay? Why don't we try that? It seems like whatever we do is only going to impact this particular subtree for the root. So let's not worry about this one just yet. Okay? Let's not worry about it. Just omit. What we want to do is, for case number 4.2, before deletion, before deleting 88, what will be the in-order traversal? Okay? So it's going to be ... on the left subtree over here. And then we got a root 44. And then let me write them down. 54, 65, 76, 80, 82, and then 88, 93, 97. So guys, in case I make any mistake, please let me know. Okay? I could make a mistake. All right, that's the in-order traversal. Agree? Okay. What node are we trying to delete? 88, which is over here. That's what we are trying to delete. All right? If you want to delete this node over here, simply deleting it is not a way to go, as we said before. But what we can do is similar to what we did earlier. Remember for this guy over here. Rather than just deleting 32 over here, in some way you're replacing this node by 28, right? When you try to delete 32 over here, you basically simply delete it, and then you're trying to just have this one take over. That's in the previous case. But for now, this one you can see even more clearly. Okay? Let's say I want to delete 88. I want to replace that by a node. Which node can I choose to replace it? And I want to maintain the sorting order at the same time. How many ways can I replace it by? 2 different ways. Mention one. 93. Right? Because 93 comes after that. So if I can somehow replace the 88 over here by 93, which is over here, that may be one way to go. Or if I replace 88 by 82, which comes before that, which is over here. But can you see diagrammatically? Okay, let me say this. 82 and 93. So these are the 2 keys before and after 88. Okay? Even more precisely, think about the 82 over here. It is the largest key that is strictly smaller than 88. Do you agree? Because I know all the keys over here are strictly smaller than 88 because it's sorted. Among those, 82 is the largest. Okay? I'll go back to the diagram in a moment. And can you do a similar remark for 93? It would be the smallest that is larger than 88. Okay, I'll leave that remark to you. Okay? You want to understand about 82 and 93 very well. In the linear order, it's very obvious. You just want to see, I want to delete this node. I want to somehow replace it by some node and still keep the sorting property. The obvious choice is either replace it by something that's smaller than that immediately, or something that's larger than that immediately, either way. Okay? But now, what you're working on is still a tree. How exactly do we find these two nodes? Do you see any specialty about 82 and 93 in terms of the tree? Yes? Yeah, pretty much, yeah. So basically, you have to go to either the left subtree or right subtree and then keep going, right? So let me hand wave a little bit and I'll write it down. So think about this guy over here is the left subtree. And this one over here is a right subtree. Sorry, spelled it wrong. This will be the left subtree, and the green one is the right subtree. Okay, these two. And then I will summarize that in a general way in just a moment. I want to find out the node that will come immediately before 88 in the in-order traversal. The way to do that would be you want to search for the left subtree and then go for the rightmost node. That's the way to find it. All right? In that way, you're going to find this guy here. Rightmost node of left subtree. Similarly, if you want to find 93, you're going to find over here, this is the leftmost node of the right subtree. Let me generalize this so you can feel hopefully a little bit more comfortable. Okay, so we'll talk about binary search tree. Let's say this is the node, P, that we want to delete. In general, P, in this case, has both the left child over here and the right child, right? So this would be the left subtree. And this one over here will be the right subtree. Each one of them can be arbitrarily complicated. Okay? And what we are really doing is we're basically locating this particular node over here, for example. This node, let's call that N1. And then you've got another node over here that's a leftmost node on the right subtree. This one over here is actually N2. If you think about it in order traversal, right? We talked about it in the example before. If you do in order, let me do one more. Let's say this one over here is the leftmost node in the left subtree. You know what? Let me rename them. N1, N2, N3, N4. All right? And then this is left child, LC, right child. So now how many nodes do we have? Let's say 1, 2, 3, 4, 5, 6, 7. Okay, 7 nodes. Let's focus on these 7 nodes. What will be the in-order traversal order? in order traversal, right? Start with N1, left child, N2, and then P, and then N3, right child, and 4. Right? That one should be straightforward to you. And let's say if we actually want to delete, in that way, you can see N2 over here is the largest. That's smaller than P. And N3 over here is the smallest. That's larger than P, right? So this is a more general way to see it, but of course, depending on the example, right? So whenever you're reaching this final case where the node you want to delete has 2 child nodes, in that case, you're going to find out either this node over here, we're going to find out this node over here, either way. Okay? Let's say we do one of them, and then the other one can be left as exercise for you. Question? You got a question? Oh, you're fine. Okay, good. That's okay. Okay. Let's now try to talk about this case. Okay, just this one here. I'll put it in a new page. I'll do this one here. This one's slightly more complicated, slightly. And this one here, you can do exercise, how to delete. I want to delete 17. Okay, that one's left as exercise for you. So why don't I put it here? Let's see how we are supposed to handle this case. Okay? So now we want to delete 88. 88 is over here. So this is the P. And then we go to the left subtree and go to the rightmost node. Okay, so this is R. So R over here, so P is to delete. R is the largest key that is strictly smaller than 88. Right? So these are the insights that we just spoke about. Right? So now how do we do the deletion? Okay? Let me circle these two. What you're going to do is you're going to do some replacement. Okay? You're basically going to replace 82 over here and put it here. Okay? That's the first step. Okay? Number 1, replace 88 by 82. And once you have replaced that, you can think about it as if you got this tree over here becoming an orphan tree. That one there is not too bad. All you got to do is just connect over here, and that's it. Okay? So you're going to do the replacement. That's step number 1. And step number 2, connect. Okay, so this one here, no, and this one here. Okay, we're good conceptually, right? And what's really important for you to do as an exercise, again, guys, very important, okay? Compare the in order traversal results before and after the deletion steps. There should be no surprise because you're basically still just deleting the 88 as expected. But the way we did it was by replacing 88 over here by the largest one that's smaller than it in the in-order traversal. And everything else will be similar. Okay? This case, arguably, of course, is the most complicated case you have to deal with. All right? All right, any question? Yes?
Is there a specific reason why we
It's a very good question. It's a very sensible. It's the most, most frequently asked question. Is there any reason we would choose, for example, the largest that's smallest, rather than the smallest that's largest? No, doesn't matter which one. If you feel more comfortable doing this way, by all means, you should do it. If you want to choose this one instead, you can also do it. Both of them should really give you the same result in terms of the in-order traversal of the resulting tree. Okay, I'll put it down. It's an important remark. I'm glad you asked. Choosing 82 or 93 works. The resulting in-order traversal are identical. The tree structure might be slightly different, but the in-order traversal sequence should be the same. All right? That's an important remark you want to also understand. Yes? No, you cannot do that. Let's say, for example, if I understood you correctly, you're saying replace the ADA over here just by this particular subtree. Is that what you meant? Yes. Okay. It wouldn't work. I tell you why. That means you gotta delete this link. So you got this link over here, right? But the problem is, what happened to this?
Yes, so I'm saying that if the rightmost subtree, all keys are greater than the leftmost subtree, everything like the 97 will all.
You mean put it here? You may do that, but I can tell you that in this specific case, yes, it might work because you can see the diagram. Indeed, you might find a way that's to find neither this nor this and then complete the deletion. But it only works for a specific example. It wouldn't work in general, meaning that it's hard to really write a general method to really handle that. Yeah. So I would say the standard way is really to say, well, the reason that we can, let me just put this as a concluding remark. The reason that we'll choose either this or this, very simple reason. Let's say if you got this particular sequence over here, I want to delete this. I want to know what I can replace this original node by. Obvious choice would be either to replace by its predecessor or successor. Right? If you got any other way that could be very specific to the tree you're given, would you not be general? Mm-hmm. I hope that kind of answer your question, right? Okay. Okay, yeah, so if you go back to the slides, that's basically what we said. You can take a look at exercise about if you choose another one, right, which I already discussed. Okay, running time will still be dominated by the searching process. So it will still be big O of H. Worst case, big O of N. Okay, so these were the two cases we talked about. And then some exercise for you, programming-wise. And that's it. Okay, that's the end of binary search tree. And guys, any question? We good? Okay. Okay, so we got about another, hopefully 25 minutes, and then we can finish more, okay? And then before this short break. So what I would like to do is I want to move on to a new lecture, okay? And the lecture, let me just keep that slide handy just in case you want to ask me later. All right, so this will be the last lecture series you have to study for the exam. I'm going to cover part of it today, and the remaining part will be makeup lecture for you to compensate for Monday, the test, as usual. All right, so they're going to be ideas about priority queues, heaps, and heap sort. Right? Heaps and heap sort will be the makeup lecture contents, and I will talk about priority queue today. And before that, we also talk about one important concept called balanced binary search tree, which is also important. Okay, let's get there. So we're going to talk about, again, worst case running time and best case running time for the binary search tree. Okay, especially we want to focus on worst case to see how it actually happened. And there is another property you want to know for tree. It's called a height balance. We learn about search property. We learn about sorting property. Now there is a third property for you called height balance. Okay? This one here is not necessarily for binary search tree. It's just for binary tree in general. And heap that you're going to learn in the makeup lecture is such a tree that is going to maintain the height balance property. I'll make sure I write this remark maybe at the end. Okay? But we'll get there. And then I'll discuss what priority queue is in general. Pretty simple concept. I just need to make some observation about what's really the difference between normal queue, FIFO queue, and also priority queue. And then we can, if time permitted, we can talk about how you can implement priority queue using a linked list. Surprisingly, they are very analogous to the insertion sort and deletion sort that we talked about earlier. I'll try to hopefully talk about it. Okay, we'll see. And then for the heap and heap sort, that'll be for your makeup lecture. Okay, that'll be it for the whole course. Okay. Okay, let's now talk about the balance first. Okay, we'll talk about if you want to do insertion for binary search tree, you have to do searching first. And the search is going to have big of H. In the worst case, it's going to be big of N. I just want to talk about very quickly about how this is possible, right? So these are just 3 examples. I'll do one of them. You can do the other 2, okay? Let's say this. I want to have a binary search tree. And I'm going to insert the keys in this particular sequence. Before I ever visualize the insertion, can you imagine how the tree is going to look like from here? I'll start you with. If I do the first one, 100, it's just going to become the root. Okay? What about the second one, 75? Should it become the left child or right child? Left child, agree? Okay. What's going to happen is we're going to do some binary search from here, and then it's going to return this particular external node, and then it will become 75, right? That's what we said before. So that one there is going to be 75, and then 68, smaller than, so 68, sorry. I might just need to move that a little bit. Oops, sorry. Tricky. You know what? Let me just redraw. Okay, we'll start with 100, and then 75, and then 68, and then 60, again, smaller than, and then 50, and then 1. This is a binary search tree, by the way. Okay? This is a binary search tree with the heights big O of n. Because you can see the height will be 1, 2, 3, 4, 5, which is linear to the number of nodes in the tree. All right? It's a very important insight to note. And the exercise for you, pretty easy. Try to draw these 2 as well and convince yourself. They're also going to, in different order, but still going to give you some linear tree heights. Okay? And the point from this page over here is to say it is possible to have the worst case for searching being linear. Searching, insertion, and deletion can be big O of n because the height is linear. Okay? Okay, that's one. And then let's now move on. Okay, this one, let me go over a little bit more slides and then we'll talk about it. Okay, now we'll discuss a height balance property. Right, so these are the example you're going to do, right? And, okay, there's something you want to note over here. To avoid the worst case running time, when your tree somehow becomes very slanted, like a linear height, the idea would be you want to take actions as soon as the tree becomes unbalanced. That's the general principle. And when you study the heap data structure, it's going to follow this kind of principle. You will see how we do insertion and deletion. After each insertion or deletion step, you're going to do something to restore the balance for the tree. That's what you will see, okay, in the makeup lecture. Okay, let's see the definition. Let's say you give it a node, P, and then the height of the subtree of P. Okay, let's see this. Okay, that's the definition of height, right? We talked about this already before. So this one here, you got to make sure you review. What does it really mean for the height of the tree? Basically, the maximum depth of the nodes. And what does it really mean when we say the high balance property that's satisfied by a tree? As easy as for every internal node n in your tree, their heights, the heights of their child nodes should be within 1. Okay, what does that mean? Let's now take a look. What we have to do is to annotate the heights of the tree. Okay, let's start with this one over here. Let's look at this tree. Okay, this tree over here. By definition, every external node has the height 0. 0, 0, 0, 0, 0, 0, 0, 0, 0. Pretty easy, right? And then from there, we're going to do bottom up. What about the heights for 51? The heights of the maximum height of the child node plus 1, which will be just 1. What about the heights for 48 over here? 2, right? The maximum height for the child node will be 1 as opposed to 0, and then plus 1, plus the edge. So that one will be 2. Okay? What about height for 77? 1. What about the height for 56? Maximum will be 2, plus 1, 3. All right, and height for 5 over here should be maximum 0 plus 1. And 32 over here, maximum 0 and plus 1. And 17, maximum will be 1, plus 1 will be 2. Finally, what's the height for 44? Maximum will be 3, plus 1, 4. You want to get used to this annotation process. You will need that to judge if a tree is balanced. That's the best way. Once you have done the annotation, you have to look at starting from the root. It's a recursive process. This root over here has 2 child nodes. This and this. You want to make sure the absolute value, 2 minus 3, right? You can see the 2 here and the 3 here, should be less than or equal to 1. That's by the definition, right? What about for this particular node? It has these 2 child nodes. And then you have to check to see the heights is 1 minus 1, right? You can see 1 here and 1 here. Is it less than or equal to 1? It is. So it's still satisfying. And then similarly, if you look at, let's say, these 2 child nodes, the height difference will be 2 minus 1, which is 1. It's still less than or equal to 1, right? You're going to do this kind of a checks throughout the tree. If every if the 2 child nodes for every internal node has their height difference less than or equal to 1, then that means your tree is balanced. In order to check it, you have to make sure it annotates the heights for each node properly first. That's what you want to start with. Okay, any question about this before I need to do something slightly more extension to it? Okay, any part that's confusing to you or anything you're not following? Now will be the time to ask. Okay? Yes?
Just make sure I understand correctly. So based on the lower limit, or based on the number of nodes on each side, you determine if it's balanced based on the lowest one. And if it's both sides of the node are equal, like.
Basically, for every internal node, for example, this is internal, you look at the heights of their both child nodes over here. In that way, if the child nodes has their heights difference less than or equal to 1, then you're fine. If it is more than 1, in that way, you're not good. So why don't we see another example, which will show to you how it can become ill-balanced. Okay? Let's do another one. So let's say this one here. What if we try to insert 55 into the tree? Okay, now take a look at this tree over here. If we want to insert 55, how is the tree going to look like after the insertion? 55. Where should it go? $55 should go all the way to over here. Agree? So that means you're going to get 55 over here, and then it has external node, like that. Okay? And let's now try to annotate the heights like what we did before. Okay? Now this time I'm going to do a little bit faster. Okay? That's what you should do as well. So first of all, start with external nodes. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. What's the height for 55? 1. What's the height for 50? Sorry, say it again. What's the height for 55? Over here, it should be 0 plus 1, 1. What should be the height for 51? 1 plus 1, 2. What about 48? 2 plus 1, 3. What about height for 77? That one should be 0 plus 1, 1. Did you already realize we got some violation for the height balance already? Okay, if you haven't seen that, that's okay. Let me finish this. What about the height for 56? Maximum 3 plus 1 will be 4. Okay, we're done with the right-hand side. So 0, 0, this should be 1. 0, 0, this should be 1. 1, 1, this should be 2. And 2, 4, that should be 5. Now, how many violations do we have about the height balance property? This is 1. These two child nodes. And also these two child nodes over here. And also these two child nodes over here. Right? These are the violation. Number 1, number 2, and also number 3. For example, why is number 1 a violation? The height balance property. Because if you try to calculate the difference, 2 minus 4, the absolute value is strictly larger than 1. So it violates that. If it's smaller than or equal to 1, then it doesn't violate. Okay? So in the exam, a very basic question will be, start with a tree, annotate the balance, annotate the heights for every node to start with. And then I might say, now try to insert or delete certain nodes. After that, you'll try to argue whether or not the resulting tree is still balanced. And the way to show that is, you want to annotate the resulting tree's heights for every node. And then if there's any violation, you want to identify every one of them. Okay? Okay, so what we should do now is exercise for you. Try to see, starting with the same tree over here, if you try to insert 63, is it going to result in a tree that's not balanced? Okay? Give it a try. Okay? That's exercise for you. Okay, so that's about this tree height balance. Any question about this? Yes, Varys. Very good question. Let's say if we knew that inserting 55 is going to violate the height balance property, do we actually allow user to insert in the first place? Yes, we still allow them to do it. What's going to happen is, once we have done the insertion, you as an implementer, you are supposed to check to see whether that particular insertion is going to violate the height balance property. If it does, you have to do something about it to restore the balance. Okay, and that's something the heap data structure will actually show to you, how you can do that. Okay, I'll write down the remark. After it's detected that the insertion caused a violation of the height balance property. Height balance property. Some steps. Okay, sorry, I'm running out of space. Some steps, okay, continue from here. Some steps should be taken to restore the balance. That's something you will see when you study the heap data structure. But the short answer is yes, even though the deletion or insertion may violate the high balance property, but you'll still do it. After that, you're going to actually restore the balance by certain operation.
Is that the extra lecture that you said?
Yes, the makeup lecture. I'm going to make it available today. Yes, good. Okay. All right, if no further questions, I'm going to start with priority queue, which is a very simple concept. I just need to clarify some common confusion very quickly. So what is really a priority queue? Let's go over just the slides very quickly, and then I can annotate some observation for you. Okay? And then I think we should have time to really talk about very briefly how you may implement the priority queue using singly linked list, for example. But I can give you the conclusion right away. Typically, in practice, if you want to implement priority queue, singly linked list is not the way to go. What's the common way for implementing priority queue? Heap. That's why you got to study for that. Okay, but for completeness, we can learn about why singly linked list is not really a perfect solution running time-wise. We're going to see that. Okay, let's go one thing at a time. So what is a priority queue? In some way, it's like a queue. It's going to store a collection of objects. But here, object here, let's be more precise, is like an entry. Do you guys remember what an entry is? Right? We talk about binary search tree when we talk about entry. Entry has a key and a value, right? Similar. And in the case of binary search tree, the key is used for searching purpose, so it cannot be duplicated. But in the case of priority queue, the key is not for searching. It's only for denoting priority value. The lower the value, the higher the priority. That's something we'll see. Okay, I'm just talking about some details you will learn. Okay, this is one example visualization of priority queue. It's a collection of entries. So when you look at the diagram later, okay, let me show you very quickly. Okay, so for every entry, you can think about, for example, one over here, this is the key denoting the priority. On the other hand, the element over here is the data. Well, just an element. And it's good to clarify right away. The lower the value of the key is, the higher the priority is. So now you can see number one, this is the entry with the highest priority. On the other hand, you can see this is the largest key value. This is the entry with the lowest. All right. And one thing to note, the keys denoting the priority do not need to be unique. They can be duplicated. For example, if you look at this one here and this one here, entries with the same priority. Let's say all the other higher priority entries have been selected. Let's say it turns out 3 is the only thing that's, let's say this. Let's say we already got rid of this one, these two already. So now 3 is the lowest value, highest priority. Does it really matter which one we choose? No, it doesn't matter. You can choose just one. Okay? When needed, doesn't matter which one's chosen. Doesn't matter which one's chosen. All right, so these are all important facts about priority queue. Okay. Okay, and what kind of operation can you do? You can do insertion, inserting some entry into the priority queue. You can try to remove, and remove is very important over here. Remove means you want to remove the entry with the highest priority. the highest priority, okay, i.e. the lowest key value. Okay. And let me see if I miss any point. And then I'll go back to the slide, just a moment. I want to make sure I mention every important point to you. Okay, what you really want to compare is a priority queue with a FIFO queue. Compare priority queue with a FIFO queue. Okay? Over here. Let's talk about something we know already. Well, let's say, okay. Entries in a FIFO queue is returned in the so-called chronological order. The earlier you were inserted into the queue, the earlier you will be extracted, right? First in, first out, okay? On the other hand, entries in a priority queue is returned. Doesn't really matter how early you were inserted into the priority queue. It only depends on the priority, the key value. Is returned according to the key value. All right, so what you really want to compare would be chronological order versus key value. All right, so these are the 2 points. Okay, so everything has been set. So these are just some examples. For example, let's say this. If there's a standby queue for the air tickets, who should really get a priority? For example, people who fly the most frequently. They might have the lowest key value, the highest priority. And let's say in a network, so let's say you got very limited bandwidth. So which activity should really get a priority? Usually the live streaming activity, like a YouTube channel, YouTube video, should really get higher priority as opposed to maybe downloading activity. Right? So just an example here. All right, so that's the ADT, so which means we're going to define the operation. Nothing should be surprising. So what does it really mean to get a minimum? Minimum means we want to get an entry with the minimum key value, meaning the highest priority. That's the min, okay? So the min here is really referring to the key value, not the priority. Minimum key value means highest priority. That one there is a little bit analogous to the front of the queue. Little bit, not exactly, okay? And the size, obvious, number of entries in the queue is empty. Check to see if there's any item there. What about insert? Just insert the key and value pair into the priority queue. It is okay to result in duplicates in the key. That's okay. And finally, we got remove min. So that means not only that you want to know what's the entry with the lowest key value, you want to remove it as well. Okay? So these are the typical operations you will need to support if you want to implement the priority queue. So the last discussion I would like to have, maybe a few minutes, is to see how we can implement these operations by using singly linked list, for example. Okay, and then we're done. Okay, let's take a look. All right. So this is something we can take a look. So let's say we got 2 strategies for implementing priority queue. Either you try to maintain some singly linked list that's always sorted, versus you try to maintain some unsorted list. So these are the 2 possible strategies. I'll visualize to you in a moment. But what you really want to compare later is the strategy number 1 is really like how insertion sort will work. And strategy number 2 is really like how selection sort will work. Right? Let's compare. And I do have a table over here to go over. Okay, let's take a look. That'll be the final part I would like to talk. about your course contents. Okay, maybe 5 minutes. And then we'll take a very short break, and then we'll do exam info. Okay, so we want to talk implement priority queue. And then we have the methods that we want to support for the priority queue. The size is empty minimum, insert, remove min. Again, minimum over here really means the highest priority. All right, over here. And there are two approaches. Okay. Here you got sorted list versus unsorted list. This will be one possible way to implement a queue. This will be another possible way to implement a queue. Okay. In approach number one, if the list is actually sorted, that means if you find any adjacent entries over here, for example, these two entries, and their key values must be sorted. So that means Ki over here must be less than or equal to Kj. That's something we want to maintain. It's basically sorted according to the key values. Okay? In that way, if I want to find out, for example, what's the minimum key, where should it be? Here. So if I want to find out the entry with the highest priority, I can just go to the head of the list. That's it. On the other hand, unsorted list solution doesn't care where the keys are sorted. They simply don't try to sort them. So you cannot say anything about adjacent keys over here. So is the head of the list the minimum key? Not necessarily. So you cannot make that assumption. Right? So these are the two approaches we are trying to do. Let's now compare them. Okay. Size is empty operation. Pretty easy. Just want to know what's the size of the list and if the list is empty. They should be just constant, right? These are easy. What we want to know is about the minimum. As I said before, for the sorted list problem over here, it's almost like selection sort. Sorry, it's almost like I will let you do the analogy when you actually think about these two approaches. I'll let you think about the sub-steps. Maybe that should be some nice mental exercise for you. For now, let me just go directly to how you can analyze this. For the minimum, I can simply grab, for the first approach, just the first node because I know it is sorted. Right? So that one there will just be big of 1. What about if this list is not sorted? In that case, I just need to run a loop to go one by one and find out what the minimum is. And that step corresponds to selection sort or insertion sort. Think about it. Okay? That one there will be linear. Because if the list is unsorted, how can I find out the minimum? Well, write a loop. Right? Now, I want to insert an entry into the priority queue. For approach number 1, I cannot just insert the new entry into the first one, for example. I cannot do that. That might break the sorting property. So what I should do is I should really go one by one until there's a right spot for me to insert into. And think about what that step is really corresponding to. Insertion sort or selection sort. Okay, think about it. So now to really insert to the right spot, that will take some loop. So that's why it's linear. On the other hand, if the list is unsorted, doesn't matter where I put it. I can put it at the last or put it at the first. Doesn't matter. So that one there is cheap. Just big of 1. All right, finally, how can I find out the entry with the minimum key value, i.e. the maximum priority? So I can, for the sorted list, I can just remove this one here. That's guaranteed to be the minimum. Right? So this one is guaranteed to be the minimum key, which is the highest priority. Okay? By choosing it, just big of 1. What about for this one here? Well, this one here, you got to choose the minimum and then remove it, right? And the minimum can be here, can be here, can be here. You simply don't know. So you need a loop to actually go over and remove it, right? So that's why it would be big of N. Well, you can see from these two approaches, doesn't matter which one you might choose, you can see some linear somewhere. We don't want that. So by studying the heap data structure, you will see that we are able to improve the performance from big O of n down to log n. That's what we'll see. All right? So this will be the last part I would like to talk about for this course. And then for the makeup lecture, you'll continue from here and then talk about how we can use the heap data structure to implement priority queue. And you want to pay attention to this particular table. Once you're done with the heap study, compare each operation to the heap and then to see how they perform, how they improve the performance. All right? All right, any last minute question for me? You can ask me later in the review session, but just for now. Anything you want me to clarify? Okay, everybody's good? Okay. Okay, I think we got 14 minutes. If I may, another 2 minutes, I do have some very quick wrap-up slide to wrap up the course. And then we do that, take a 2 minutes break, and then we'll talk about exam. Okay, we'll still finish in time. Okay, so this is where we are. Okay, let's see this. Okay, wrap up the lecture. Okay. Just some not necessarily exhaustive list about what you have learned, but at least the important topics. Programming, we talk about JUnits and recursion. We did a lot in this course, right? Generics as well. And data structure, we did a lot about arrays. We dive deeper into how you can do insertion, deletion of the array, right? And these I put in parentheses. These are the optional topics in the Q's lecture. For those of you who are interested, maybe after the exam, you may want to dive into them to learn a little bit more, okay? Not too sure if they will even cover them maybe in the 31-1, maybe not. So for your knowledge, you can consider. And we talk about singly linked list versus doubly linked list, right? You want to know very well about their difference before you come to the exam. Stats and queues, and also trees, binary tree, and also balanced binary search tree. You can see we got so many variants. Trees, binary tree, binary search tree, and balanced binary search tree. So many variants. Be very clear about what kind of property each one of them is supposed to satisfy. Okay, priority queue, which we just spoke about. And the heaps will be something you will also learn from me, but offline from the video. Okay. And algorithm. What kind of algorithm did we learn? Asymptotic analysis, make sure in the exam you know both, number one, how to count the primitive operation, which we did in the very beginning of the course. And also, given some algorithm, how it can approximate the running time. You should know both. And binary search, and also, this is the list of algorithms about sorting that we learned in this course, right? So these are the minimum you should really know as a SE or a CS graduate. Insertion sort, selection sort, merge, quick, and heap, right? So these are all the sorting algorithms you should really know, okay? And traversal, pre-order, in-order, post-order, right? And beyond this course, right? Just some suggested activity you might want to do. Because students sometimes ask me beyond this course, what kind of exercises should I do to strengthen my programming ability? The number one I would suggest would be, so this is a very standard textbook that usually your instructor will use in 3101 in the third year algorithm course. That one there, the good thing is it contains lots of pseudocode, not in Java, not in C, just pseudocode. So my suggested exercise would be, try to study the algorithm and then try to implement it in Java and write some JUnit test cases about them. That will be the best way to really strengthen your understanding about the algorithm, data structure, and also to improve your programming ability. Doesn't need to be Java. If you feel more comfortable with Python, C#, feel free, okay? That'll be my number one exercise. And this one here is not exactly about data structure, but it's more about OO. Since we talked about OO in this course, polymorphism and dynamic binding, we touch base a little bit, not too much, but if you want to dive deeper, you can look at this one here, design patterns. That's something you will learn a bit in the 2311 software design course, but hopefully as many as possible by your instructor, but sometimes not too many. So you can consider this as well. This one is not as important. Okay, just one more suggestion. For those of you who might be interested in building a compiler, by building a compiler, I meant you can define your own programming language by specifying grammar and then given any valid input satisfying the grammar, it can transform the input to any output you like. That's what a compiler is about. If you're interested, here is one tutorial video. For those 3 exercises we have done in this course, you're ready to take this particular kind of learning for how to build a compiler. And there's actually one EECS course, 4302, building compiler. For those of you who may want to have some elective in the 4th year, you can consider that as well. Okay, so you will use tree, recursion, lots of recursion. If you want to build compiler, it's just about recursion. All right, that's about it. If you want to find out more about hash table and graphs, I also gave you some references, especially hash table, if you want to learn about it. Okay, that's it. Okay, why don't we take a 2 minutes break, and then we'll talk about your exam. Okay, 2 minutes.
Thing that the tutorial, it's from a course you previously taught?
Yes. Yes. Yeah, if you're interested, just go to the link, and then you can see the link recording for all the lectures.
Okay, so that's why I actually wanted to ask you about it. I saw that you taught it before, and I wanted to watch your lectures during this summer. Do you think during this summer is too early, or during this summer is good time, like after 2011?
I don't think it's late. Have you ever learned about context-free grammar before?
Not really.
You're in CS, right?
SE.
SE. So that one there, it's not really inappropriate. I think for context-free grammar, which I'll mention in the tutorial, you can simply just Google for context grammar. You can easily find some very nice tutorial. It's not rocket science. It's very easy to pick it up by yourself. Yes, you can definitely start with it.
First and then try.
Yes. Watching the tutorial, anything you find there's a gap, you can always Google for some self-learning.
Okay.
Yeah. Good. Okay, that's 1 more minute, and then we'll talk about your exam. Yeah, we have about 7 minutes before the next class. You definitely have time to ask me more questions about the exam if you want to. Oh, not yet. Yeah, let me go over exam guide first, and they'll take a question. That might be more effective. Okay, let's start. Okay. The PDF I'm going to present now, I'll make them available to you. Make it available to you this afternoon, just in case there's any fixes I need to do. All right. Okay, so general information exam will be Sunday, April 23rd, 2 p.m. to 5 p.m. All right. Double check with the registrar office just in case I got it wrong. That's where you should go. 50% of your course grade, and there will be an exam question booklet that will be distributed during the exam. It's in person, it's paper test. You don't use any computer. Okay? And you will not be allowed to bring any sketch paper yourself because the booklet itself does include sketch paper. I think I gave you about 3 pieces of paper at least, so that should be enough. So don't bring your own sketch paper. You will not be allowed. Okay? And hopefully you won't, but in case you really have to miss the exam, follow the procedure. Okay? And there'll be no data sheets that will be allowed during the exam. So this also allows me to give you maybe some basic definition question in the actual exam. So I think that's in some ways the advantage of not allowing data sheets. Okay? But anyway, that's the rule. You cannot bring any aid to your exam. And that your mobile phone should be stored in your bag, put underneath the table, right? That's kind of minor detail. You can bring together with snacks, water bottle, wallet, whatever. That's okay. Stationary on the table with you. Okay? I will correct you in case you did it wrong in the exam. And coverage is cumulative, as I said, on day 1 of the semester. Everything. So everything you will find on the lecture site, including the in-class lecture, makeup lecture, and also your assignments. So these are the coverage, okay? And the format, mostly will be handwritten answers. You may have to write explanation, definition, justification, or do some proofs. Okay? And then there might be some multiple choice question, might be, but may not be many, because you already got multiple choice question in your written test. May not be too many. And you may be asked to write answers in valid Java syntax. You may have to. For example, I might say, okay, now consider case 2.2 case 4.2 for binary search tree deletion implemented. I might say that. Okay, just make sure you do the exercise I suggested if you want to before the exam. Yeah, so study tips, the way I'm going to make the question will be I'm going to go over all the materials that we have gone over in the semester, and I'll make questions from there. So everything that will appear on the exam is something that we have already learned. So make sure you just review everything that you're supposed to learn. Okay. And I'll try to give you guys some example questions. Those are just example as ever, but that might help on your review. I'll try to make them available hopefully before your study day on Tuesday. Okay, so maybe after the Easter weekend, you can actually, or if you celebrate for others, you can look at that example question. All right, any question about the exam? You mean the programming test solution, we wouldn't distribute them. We not really. I think I'll try to definitely make your programming test number 2 marks available to you before the exam. Yes, that's something I'll definitely do. Yeah. But if you want to talk about, let's say, your programming test performance in general, I can still do it. Yeah. Okay. Not to the same level as the programming test. For example, if you miss a semicolon, we wouldn't deduce any mark, for example, right? We can be more tolerant. On the other hand, if you write something that doesn't even look like Java, then what can we do, right? We got to deduce mark. So I would say, as long as you write reasonable Java code, and there might be some minor mistake, of course, we'll judge to see what's really minor. We'll be reasonable, and then it should be fine. Yeah. Yeah, so in terms of difficulty, anything is possible. For exam, I would say prepare that part also well. I already gave you one example. Let's say if I say, okay, now consider case number 4.1 for binary search tree deletion. How would you do it? Right. Mm-hmm. All right, any other questions? Yeah, Faris. Oh yeah, don't worry. If I let's say, let me elaborate that further. If I really say case 4.1, I'll remind you what the context is. I might say, assuming that you have done some binary search tree, you have done some binary search on the tree, and then the return node is internal, let's say. And both childs are there, and then now in this case, I'll give you even a method header, and I'll ask you to write some code about it. Yeah, I'll give you enough context. I know you got data sheets, I will remind details when necessary. But that doesn't really mean, I will always give you 100% details, right? So there's some basic level of knowledge you should really know without the data sheets. Yeah, that's reasonable. If I do ask you, for example, to implement some binary search tree operation, I'll give you, for example, binary search tree node class. Yes, I'll give that to you. Yeah, absolutely. Okay, good question. Can JUnits be covered in the exam? I'll make your life a little bit easier to be more focused for this exam. You will not be asked to write any JUnit test cases. However, you may be asked to read some JUnit test cases and answer a question about it. A little bit like, maybe not that long. Maybe a little bit more focused fragment. I say, okay, consider this. Mm-hmm. Yes, you got to interpret the JUnit test case. That's exactly right. Yes. Yep, it's possible. Yes, indeed. Yes. Okay, guys, we still have time. Not too much, but maybe 1 minute. Okay. But nobody asked me whether the exam will be easy or hard, right? Well, you don't care. Oh, you know me. Okay, sure. I would say the exam, I'll mention that anyway. The exam will keep you busy. And I really want to see how much you have learned in the course. So take the advantage of the fact that you guys pretty late exam, really want to go over the material. I think once you go to the third year, what you learn from this course, I just hope that it will be useful. Take this opportunity to synthesize everything together. The exam is going to be long, it's going to be not easy, but you just study for that, and I hope you'll be fine. All right, thank you so much. I'll reach out to you about the review session. We'll schedule that. All right, you guys take care. Hello.